Hi everyone, and welcome back to learning about quadratic equations. Just as a reminder, in the last video, I left you with the task to find the x-intercepts or the zeros for each of these equations. If you did not complete this task, please pause the video and return to it when you are finished. Otherwise, I'm going to spoil the surprise for you, and we all want you to have your own practice. So do the task on your own and then check your answers with me. Otherwise, drum roll for the answers. Let's go through these. First equation, okay, you take your A is 4, your B is 12, and your C is 9. And you plug those in the quadratic formula, you do your simplifying, and continue, so on and so forth. And you get that under the radical, you have a 0. So the square root of 0 is just 0. And then negative 12 plus or minus 0, well, doesn't really give you two answers, right? Negative 12 plus 0 and negative 12 minus 0 gives you the same thing. So you wind up with one solution that's negative 3 over 2. You can pause to check your work with mine. Otherwise, we're going to move on to the next one. Second equation, so you plug in numbers. A is 3, B is 14, C is negative 5. You do your simplifying, you simplify your radical. Notice you get 256 under the square root, and that's perfect square, so that just breaks down to 16. Then I split my two solutions to have the plus case and the minus case. Simplify those fractions out. Oops, and you get that your solutions are 1/3 and negative 5, which means that this particular quadratic is going to have two solutions, two zeros, two x-intercepts, whatever you want to call it. Last equation, you plugged in B is negative 6, A is 1, C is 25. Notice negative B, or opposite of B, is negative of negative 6, which gives you positive 6. Other things to notice is that you get a negative number under the square root, which we all know you can't take the real root of a negative number. So we can simplify this to be the square root of negative 1 times 64, which is the square root of negative 1 times the square root of 64, which the square root of 64 is 8, and the square root of negative 1 is I. So that simplifies to be 8i. Okay, then I simplified some more by pulling out a greatest common factor, canceling out the 2's, and I get two solutions. One is 3 plus 4i, one is 3 minus 4i. They're both imaginary. Kind of similar, right? So with all that said, the point of this was to kind of examine what kind of solutions you may get from different quadratics. Okay, so this one, you had one real solution. This particular quadratic gave you one real solution. This quadratic gave you two real solutions. They're completely different. And this one gave you two imaginary solutions. Not only are they imaginary, but they're conjugates of one another. So really these are complex conjugate solutions. And if you don't remember what complex conjugate is, this is from a previous video. It just means that same two terms, opposite side in the middle. So really you have two complex conjugate solutions. Now, I want to take this into what this means on a graph. So think about it. If you have one real solution, that's like saying you have one real x-intercept. So if you're looking at a graph, what should that look like? How can you only have one x-intercept? And the answer to that would be that it just kind of touches the graph, but doesn't actually cross through. So this is one case or one equation where you'll see this happen. Another one some people brought up in class is, let's say you have x minus 4 squared equals 0. That's really x minus 4 times x minus 4 equals 0, which really your only x value is positive 4. It's just repeated 2 times. So it is technically two solutions, but it's double counted. So really there's one x value, or one real solution. Next one, so you have two real solutions. This is probably what we've seen more times than not. That means you have two x-intercepts, which should look something like this. Okay, so here's my parabola. This is my x-axis right here. It crosses one's here and one's here, which you see are at negative 5 and 0.33, which is 1/3. So again, using your graphing calculator is also a good way to check the values of your algebra that you got here. And mine matches, so I'm good. Last one, and this is probably the most interesting case. What does it mean to have an imaginary solution in terms of a graph? Okay, we've kind of introed this in class, but let's look at this graph on Desmos, and it looks something like this. When you have two imaginary solutions, that really means you have two imaginary x-intercepts. And an imaginary x-intercept just means it doesn't actually cross the x-axis. So this parabola will be completely off the x-axis, it'll never touch. That's why we have two imaginary solutions. Something to think about. Now, the point of this video is to answer the following question. And the big idea, please write this down, is how can you tell how many solutions, and many is a quantity, so how many solutions, and what type of solutions, so imaginary or real, how can you tell how many and what type of solutions you will have without doing the quadratic formula every single time? I'm just going to abbreviate that by quadratic formula, quad form. So, every single time you want to know what type of solutions and what kind they are, you could do the quadratic formula, go through all that simplifying and say, okay, I got -3 halves, that means it's one real solution. But the quadratic formula takes kind of a long time. It takes a lot of algebra, and there's actually a quicker way that you can figure out, okay, is this going to have one or two solutions? Are they going to be imaginary or real? And I want you to look at the patterns to kind of devise what we could look at in order to say what kind of solutions they are. Now notice this one has one real solution because underneath the radical you wound up getting 0. Okay, when you add or subtract 0, you're only going to have one solution. This one had two solutions because you added or subtracted 16. You were adding and subtracting a real number because you had a positive number under the radical. And in this last equation, you had two imaginary solutions because you had add or subtract some quantity, but in this case you were adding or subtracting an imaginary number. So you had two imaginary solutions, which was because you had a negative number underneath the radical. So if I look at the quantity under the radical, I can guess that this one's going to have one real solution, this one's going to have two real solutions, and this one's going to have two imaginary solutions. So if you remember from the quadratic formula, what's under the radical is our b squared minus 4ac. And looking at that is enough to tell you what kind of solutions you'll have and what type of solutions you'll have. And this is called the discriminant. And the discriminant b squared minus 4ac is just what's under the radical in the quadratic formula. Now, thinking back to our problems, please write down these rules. But if your discriminant, or what's under the radical, you take your b and square it and subtract 4ac, and that's less than 0, or it's negative. Okay, so if you take the square root of a negative, then you're going to have imaginary solutions, and you're going to have two of them. So we say that you're going to have two complex conjugate roots. So complex conjugate is another way to say you're going to have imaginary roots. But more specifically, they're the same two terms with the opposite sign in the middle. So you have two complex conjugate roots. If your discriminant is equal to 0, or underneath your radical you get 0 when you plug in b squared minus 4ac, you get one double root. So when I say one double root, I mean it's counted twice. Counted 2 times. So that's kind of like number 1. When you were looking at this equation, you got 0 underneath. So you only have one solution. It's real, but it's double counted. And the last one, if you have b squared minus 4ac, and that's greater than 0, or your discriminant is positive, you're going to get two different real roots. So kind of like our second example, underneath the radical you had 256, that was positive. We got two real roots out. They're completely different, no relationship. So please write this down. This will be really useful to examine the graph of a quadratic without actually doing the quadratic formula. You may not know what the x values are or the x-intercepts are, but at least you know where it's going to cross the x-axis or where it's not going to cross the x-axis. So let's apply this to an example, and then we'll be done with this video. Let's say you have the equation 2x squared minus 3x plus 4 is equal to 0. Now, I have a quadratic, but I don't know how many solutions it has or what type of solution it has. I don't really care right now what the solutions will be. I just want to know something about the solutions. And that's where I'm going to use the discriminant. Okay, so the discriminant is just whatever is under the radical. So what's under the radical in the quadratic formula is b squared minus 4ac. Okay, so we need to know what our b, a, and c are, or a, b, and c, but I'm just doing it in the order of our equation. Our b in this case is -3, our a is 2, and our, that should say c, not b, is 4. So we can plug those in the discriminant, we get that negative 3 squared minus 4 times our a times our c, which if we simplify that, we get 9 minus, well, 4 times 4 is 8, times 2 is 16, which is just equal to negative 7. So what this value tells me is that when I use the quadratic formula, with all the other stuff in the quadratic formula, I'll be adding or subtracting the square root of negative 7 all over yada, 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 right? So if you take the square root of a negative 7, you know that these two solutions are going to be imaginary. Or more specifically, they're going to be complex conjugate solutions. And how many am I going to have? Well, you're still going to have some value here, because your b can't be 0. And you're adding or subtracting some imaginary number, dividing by some number, so you're still going to have 2 complex conjugate solutions. So we know that this graph is going to look something like this one that we looked at before. It's not going to cross the x-axis, and I knew all of that only by looking at the discriminant, which is, again, b squared minus 4ac. Okay, so if you're solving for x values, quadratic formula is a really good tool to use. But if you just want to know what kind of roots you have, and I probably should have mentioned that roots is another word for zeros or x-intercepts. So if you want to know what kind of roots you have, that's what the discriminant is useful for. As always, I hope you took notes. If not, watch us again and take some notes. And please come and see your teacher and or I with questions. Have a good night.